Let's go ahead and start on topic 1.2, mass spectra of elements. And basically the purpose of this presentation is going to be to introduce you to the idea of mass spectrometry, and then we're going to address interpretations of mass spectra and how to read them, how to calculate some things. So the textbook pages that are going to be related to this topic are going to be 69 through 72. Let's go ahead and jump in first by talking a little bit about the periodic table and how that has to do with our mass spectra interpretations. So here we have a chlorine table, and 17 is going to be the atomic number, the number of protons. We have the symbol of Cl, and then we have this number 35.45. And so what is this number and where does it come from? And the answer to that is mass spectra. It's the average atomic mass, and we're going to be able to calculate that using mass spectra data. So basically, mass spec is going to be a technique used to identify the isotopes of an element and their relative abundance in nature. And so the next question then becomes is, what is an isotope? So let's go ahead and take a look at the periodic table to help us understand what isotopes are. And so again, remember isotopes, same protons, different neutrons. So how do we find this? Using the periodic table. If we go ahead and look at the periodic table, it's going to give us a lot of information. So any atom with exactly one proton is going to be defined as hydrogen. Okay, if you see the one right here, that's the atomic number, number of protons. Let's say that we have 6 protons. Okay, any atom with 6 protons is going to give us the atom carbon. 17 protons is going to give us chlorine. And so these values are corresponding to the atomic number on the periodic table, which simply represents the number of protons in the nucleus. However, we can have a different version of the same element, and so these variations are going to be known as your isotopes. So isotopes have the same number of protons, but they differ in their number of neutrons. So let's go ahead and take a look at an example to help us kind of explain what an isotope is. So in nature, chlorine, which again, I'm going to go ahead and circle it on our periodic table here so we can make sure and hone in on that. Chlorine can exist as 2 different versions. So we could have chlorine 35. Okay, this number at the end just means that it has a mass of 35. But we could also have chlorine 37. And so it's a chlorine atom. So that means that it has to have 17 protons because that's the atomic number. And so in order to find the number of neutrons, basically what we're going to do is we're going to take the atomic mass, which for the first one is going to be 35, that's protons plus neutrons, and we are going to subtract the number of protons, and we should get 18. So chlorine 35 has 18 neutrons in it. Okay. So now if we look at chlorine 37, again, we're going to take the atomic mass, we're going to subtract by the same number of protons because it's a chlorine atom, it has to have 17 protons. And that's going to leave us with 20 neutrons. And so if you note, okay, this chlorine atom can have 2 different versions, okay, one with 18 neutrons and one with 20 neutrons. And so how we get that average atomic mass is we're going to average the 2 masses that we can have, which is 35 and 37. But you're going to note that the average of 35 and 37 would be 36. And on the periodic table, chlorine's average atomic mass is 35.45. So it gets a little bit more complex because we have to take into account how abundant each of those are in nature. And in order to have an answer closer to 35, we should realize that chlorine 35 is going to be more abundant than chlorine 37. And I'm going to show you how to calculate it in a couple more slides. So now the question is, like, how do scientists do this? So what is a mass spectra? How does it work? And so basically, chemists have been able to determine the various isotopes of an element and their relative abundances using this technique as known as mass spec. So this method allows scientists to find out what percentage of an element is found in nature exists as isotope A versus isotope B, for example. So in mass spectrometry, a small sample, let's say that we have zirconium, is first heated. So we have our sample that's going to be right here, and it's going to be heated. And when it's heated, We then turn it into gas. It's free floating, and we bombard it with electrons, which can knock off some electrons from the atoms, and that basically ionizes them or creates a charge. Once they're ionized, the atoms can now carry a charge, allowing them to be accelerated through the electronic plates. And so you're going to see this acceleration with those green arrows. So these charged ions are going to pass through a magnetic field. Okay, the magnet is creating a magnetic field, which is going to bend or deflect their paths. And so remember, okay, magnets have a lot to do with charge. And so the extent to which the ions are deflected are going to depend on their mass. If you think about it, it's a lot harder to move something that's bigger than it is to move something that's smaller. And so ions with the greater mass are going to be deflected a little bit less, while those with the smaller mass are deflected more. And so as the ions move through the magnetic field, they're going to hit different parts of the detector based on how much they were deflected. So the more ions that strike a specific area of the detector, the more abundant that particular isotope is in nature. And so from this, then scientists can generate a graph showing the isotopes present and their relative abundances. So on a graph, you can see this type of graph on the right. You're going to have a horizontal axis that's going to be typically labeled with atomic mass or charge to mass ratio. They all mean kind of the same thing. And ultimately, it's going to enable scientists to identify those isotopes and measure their abundance by ionizing atoms, accelerating them, deflecting them with a magnetic field, and then analyzing where they land on that detector. And so the resulting pattern tells us which isotopes are present, and it tells us in what proportions they are present. And so we're going to use this data to be able to figure out what element we're looking at. We're going to be able to figure out how many neutrons are in each isotope and various ways in which the AP test is going to test this knowledge. And so let's go ahead and break down this graph. And so first off, you're going to see the bars. And however many bars you have on the graph is going to represent how many isotopes you have. So in this case, we have two different types of isotopes for the element chlorine. The next thing that you're going to look at is you're going to go down, straight down from the bar on the x-axis, and it's going to tell you how much mass are represent each of these isotopes. And so for this one, we have a chlorine 35 and a chlorine 37, which I've already mentioned. And so those are the two types of isotopes that we have and the masses for them. The next thing that you're going to look at is the height of each of those bars. And you're going to go over to the y-axis, and it's labeled percent abundance. And so the height of the bars represent the relative abundance. And so if you're looking at the 35, that's going to represent about 75% of all chlorine atoms in nature. And the remaining, the 25% that's left, are going to be represented by that 37 mass. And so that's going to tell us how common they are. And then finally, of course, look at your axes labels to make sure that you know what it's giving you. It could be mass, it could be mass to charge ratio, it could be M to Z, which is mass to charge ratio, could be atomic mass. Just make sure that you take note of that. Your y-axis could also be labeled percent abundance or relative abundance, and we'll get into that differentiation in a second. So let's go ahead and jump right into the math behind this. And so how do we interpret a mass spectrum of an unknown element? So what is the average atomic mass of this element? And that's what we're going to try and answer. And so the first thing that I want you to do with these types of questions is I want you to go ahead and make sure that you can kind of figure out, it already gives you the mass, but you're going to want to figure out the relative abundance for each of those bars. And so what I'm going to do is I'm going to go ahead and write out the relative abundance above each of those bars based on the y-axis, so then I can easily transfer that to my math that I'm going to do. So for the first one, it's not quite at 0.1. It's pretty close though. So I'm going to say that this is at 0.096. Again, you could have a slightly different number than that, but that's kind of where I think that it's going to be at. The next one, not quite at 0.08, but very close, so I'm going to go 0.078. For this one, 0.238. This one's right at 0.5, and then this one down here, I would say, is at 0.082. Again, your numbers could be slightly different, but you're going to want to be as close as possible to what the actual numbers are in order for you to use them and get as close of the answer as you can. So now, once you have this information, basically all you're going to have to do is you're going to multiply the mass by its relative abundance times 0.096. And if you do this, you can plug it into the calculator. You should get 7.32. All right, and you're going to do this for all of the different isotopes. And so I'm going to go ahead and do that, and then we will skip forward. And so once you do this, what you're going to do is you're going to add up all of your results. And once you add up all of your results, you should get 78.57. I'm going to round this to approximately 79. And so this should be the average atomic mass that you should find on your periodic table, somewhere around 79. And so you look at the periodic table and find the element closest in atomic mass to your calculated value. And what you should get is you should get selenium as your average atomic mass of 78.97. No other element on the periodic table has an average atomic mass close enough to 79 that we could definitively say that's what it is. And so that's how you interpret the mass spectra of an unknown element. And so on the exam, you could have three different types of problems. You could have one, estimate the atomic mass from a mass spectra. This could be a real element. It could be a fictitious element. So you're just calculating it like we just did. Two, you'd need to identify the element from the mass spectra. I'm going to show you how to do that. And then three, you could have to identify the isotope from the mass spectra and say maybe calculate how many neutrons are in that specific isotope. And so we're going to go over each of these three different types of problems. So the first one is going to be to calculate the approximate average atomic mass of chlorine. And so we're going to do that just how we just did. First, you're going to identify the isotopes, masses, and percent abundances from the graph. And so what I'm going to do is I'm going to go ahead and label the percent abundances as 75% and 25%. So now the difference between this problem and the problem we just did was the problem we just did had relative abundance, and relative abundance is going to be in decimals. Percent abundance is in percentages. In order to calculate these problems, you have to change the percentages into decimals. And so what I'm going to do, that's step one. For step two, I'm going to multiply each isotope. So we have 35 times its relative abundance, not its percent abundance. So I'm going to change that 75% into 0.75. And I'm going to multiply 37 by 0.25. And then what you're going to do is you're going to add those two results. And when I add those two, I should get 35.5. If it wants an approximation, the percent abundance isn't super specific over here. So I would say I would probably round this to approximately 36 as your approximate average atomic mass, which is pretty close when you look at the periodic table. Now, two ways you could do this in your calculator. You could do this in a two-step problem. So you could use this, you can multiply it out, equals 2, and then get your answer. Then you would go 37 times 0.025 equals, get your answer, and then add those two up. Or you could do it as a one-step problem in your calculator. If you do it in one step like I did in this problem, make sure that you use your parentheses so that your order of operations is happening in the correctly, so you don't get the wrong answer. Next type of question is which element's mass spectrum is shown in the graph. So now this one, you could do it a little bit faster. You don't necessarily have to calculate the exact average atomic mass because it's not asking you to. And so this would be a way to save time on the AP test. And so the first step you're going to do exactly the same way. You're going to identify the isotopes' masses and percent abundances, and then we're going to use an estimate because we don't really have to calculate everything. And so if I were to guess an average abundance here, I would say this represents about 90% of all of the average atomic mass of this unknown element. And then for the other two aren't very abundant, and so I'm just going to say that overall together, they represent about 10% of the abundance. So because 39 is so much more abundant than the other two masses, I would say that the average atomic mass is going to be pretty close to 39. So it's going to be 39, a little above. A little higher than 39, but very close to 39. So now what you're going to do is you're going to look at the periodic table. And if you look at the periodic table, you're only going to find one element that has an average atomic mass that's a little bit over 39. And so what you're going to do is you're going to find that the only element that is a little bit above 39 is going to be potassium. And so the answer to that question is which element's mass spectrum is shown in the graph. It's going to be potassium. And finally, the last style of question that you could say, and this is probably going to be the harder of the three questions that you could potentially see, it's asking you to identify the element, and then it's going to take you a step further. You're going to need to figure out the number of neutrons in the atoms represented by the peak at 74 AMU in the mass spectrum. Now, this could keep out the identify the element part because it's kind of assumed that you're going to have to do that in order to figure out the number of neutrons. So what we're going to do is we're going to focus on this peak at 74. And the first step that we're going to do is we're going to need to determine the element represented. Okay, we're going to have to identify it because then we're going to have to figure out how many protons are in the nucleus so that we can figure out how many neutrons there are. So if we look, I'm going to use the estimate technique since I don't have to actually calculate the exact average atomic mass again. And when I'm looking at this, I'm seeing that I have about 50% is going to be 70 and 72. And then I have about 50% is going to be 73, 74, and 76. So basically 50-50. So right in between that is going to be 72 and 73. So my estimate for this is going to be that the average atomic mass is going to be somewhere between 72 and 73 AMU. And so once we get that, what we're going to do is we're going to go to the periodic table and we're going to try and figure out if any element has an average atomic mass somewhere between 72 and 73. And if you look closely, you're going to see that germanium has an average atomic mass of 72.63. It's the only one on the periodic table, so that's the element that we're looking at. Also, you're going to want to note that the atomic number for germanium is 32. That's going to be important in being able to calculate the amount of neutrons. And so, to answer question number 1, okay, you're going to want to articulate your findings. And so, what I wrote for that answer is the atomic mass of the element is between 72 and 73 AMU based on the estimation. Ge is the only element whose average atomic mass is close to this, so this is the spectrum of germanium. Now what we're going to do is we're going to determine the number of neutrons by subtracting the atomic number from the mass number. Okay, and so remember that it's asking us about the peak at 74 AMU, so our total mass is 74, and we're going to subtract the number of protons. Again, the periodic table tells us the number of protons based on the atomic number, and the atomic number of germanium is 32, so we're going to go 74 minus 32, and that gives us 42 neutrons. So the number of neutrons in the peak represented by 74 in this mass spectrum is 42 neutrons.